So our next speaker is Christian Frankenberg from JPL and Caltech. And I'm not sure what Christian is going to do because as of yesterday he hadn't made his mind up. But I think he's going to give us an overview of the instrumentation for measuring column carbon dioxide and chlorophyll fluorescence as it will be made, as it is being made from OC0-2 and as it, we hope, will be made from OC0-3 on station.
Thanks, Dave. And as he said, I haven't made up my mind yet until yesterday, or maybe I should say maybe he didn't tell me yet what exactly he wants me to talk about until yesterday. So that's also an excuse why this is kind of a potpourri of different slides, and I haven't really had a lot of time to prepare for it. But I'll be talking about not OC0-2 2/3, but OC0-2 2 and 3. Where one ended up, you probably know, most of you. It's a global view on the carbon dioxide and solar-induced chlorophyll fluorescence. And this is work of many, many people, all of which wouldn't really fit on this slide, so I can only talk on behalf of many people that are in the OC0-2 project and the TCON teams, of course, as well. And just to tell you, this is actually a graphic that we came back with from our KISS proposal that we did, I think, 3 years ago now, Michelle? Yeah. I'm not sure on the fluorescence itself. So just we have some funding, we had some funding available to get a graphic artist to actually work on this. I'll quickly go through this because this is, I mean, we talked a lot about instruments designs and just a little overview on the OC0-2 mission architecture. It's a 3-channel grading spectrometer measuring in the shortwave infrared. It has its dedicated spacecraft, so this OC0-2 is not like the ISS. We are sitting on a single spacecraft and basically can command everything. It was launched in a Delta II launch vehicle after the launch failure of both OC0-1 and Glory. They decided to really switch the rocket. And then it went into space. It's flying in the A train right now. And I think we can forget about this part here in this talk. The good thing is it was launched successfully with the Delta II. So how do we measure basically CO2 from space with OC0-2, and then also OC0-3 will basically be the same principles. We collect spectra of CO2 and O2 absorptions in reflected sunlight over the globe. So what you see here is a sketch. We basically use the sun as a light source. The photons reach the atmosphere and the surface, they bounce back, and this is the light that we measure. And this is an image of the focal plane arrays with the O2A band, the weak CO2 band, and a strong CO2 band. I'll get back to this quickly thereafter. And what we use these spectra is we retrieve the variations in column average CO2. Basically, the final quantity that we derive is a dry air mole fraction, xC02, which is kind of as if you would just add up all the CO2 molecules that are above you in, say, like a square meter column, and then you divide it by all the total amount of air molecules that are in the same column. And when you ratio this, you get kind of the dry air mole fraction, xC02 in a column average sense. So we do that by generating synthetic spectra that we try then to fit to the actual spectra that we measured, and then we update the state vector. The state vector includes not only kind of CO2 variables, but it includes also things like surface albedo, spectral shift and squeeze, and also aerosol and cloud parameters that are fitted alongside with it, using 3 bands together. And then at the end, of course, there's a validation chain, because as Leslie mentioned, we have to be incredibly precise, or I should better say accurate, to really inform us on the global carbon cycle, because it is probably one of the most demanding measurements that we can do from space so far, because we really look at the sub% variability in a quantity. It's not like we want to know whether it's 270 Kelvin or 275 Kelvin. It's really tiny variability between like 370, 371 ppm, which is hard to do. So what do we measure? Again, a zoom up on the spectral range that we cover. These are actual TVAC data that we took at JPL. You look at reflected sunlight. This is the oxygen A band. You see it here in grayscale, the deep absorption features in the oxygen band. We have one weak CO2 band, which is this one. So you see here that the absorption lines are not that deep, and we have a strong CO2 band that are way deeper. And there was a question earlier on the aerosols. Basically, the idea of having the oxygen band, a weak band that is less sensitive to aerosol variability, and a strong band with which you can get some aerosol information out of it. By using all 3 bands together, in principle, you get information on both the CO2 content, but also on the aerosol distribution, at least to some degree. Maybe what's important to note is, coming back to the column measurements of CO2, that we can't really do profiling at all. And that makes it a little bit more complicated in a way that, of course, the surface variability of CO2 is much higher than the variability that you see in the column. This is a slide that Paul gave me. This is basically if you look at the FTS data at Park Falls and you look at surface variability across the seasons here with a summer drawdown. Like this, you have a pretty high seasonality in the surface data from the tower. What you see in the FTS column average sense is basically this dampened signal. I think in this case it's about 3 times less of a magnitude than what you see in the surface. So in principle, we can't really say how the profile looked like. So this is something that has to come in as knowledge in the inversion scheme later on, because we just average CO2 across the entire column. So it is somewhat more difficult. This is now a slide, an animation that we made for more public relation purposes from real OC0-2 data, the CO2 distribution. It's kind of nicely smooth now because there was a pretty strong smoothing filter across it. But I don't know where we are right now on the date. So we are here in February, March. You see the buildup of CO2 basically over winter in the northern hemisphere. This might be related to some biomass burning in this area, but don't interpret everything that you see there. So you see the change in coverage as well. So now that we go to boreal summer, we basically cover the northern hemisphere much better. And now the drawdown period that is clearly visible in the OC0-2 data as well. So we now have kind of a year of data with OC0-2. And as Leslie said, now it starts to get interesting because you should not take that data and interpret everything like this little blob. It has to do something with that location there. It's a little harder with CO2, atmospheric CO2, because it really, as she has shown, it's influenced by weather. We don't know at what specific, it might just be that this specific point here was measured at a different time than this one, and this was just the weather pattern that's obvious in the data there. So you really have to put it through an inversion scheme to interpret the data. Oops, where am I? And that's what I call the next steps. I've shown basically the inversion scheme of how we get from like measured spectra to our xC02 distribution across the globe, of course with a little more gaps in between. But if we really want to know something about the carbon exchange across the terrestrial biosphere, we basically have to put these data into something very similar, where we don't generate synthetic spectra, but as Leslie said, we generate synthetic 3-dimensional CO2 fields. And as opposed to we operated like we put our instrument model on top of the synthetic spectra. In principle, they have to take the instrument model which describes the sensitivity of our measurements to the quantities that they actually generate here. In our case, it's kind of a column kernel, so we first have to generate like a total column average out of these data, and then we also have to take into account the vertical sensitivity, which we describe with averaging kernels. And then instead of different spectra, that basically different maps go in. So then it goes into an inverse model. And what they do is they update a state vector that includes the CO2 fluxes in space and time to basically model the distribution that we saw eventually. And what then comes out is really a CO2 flux map. But this is something where we haven't been yet with OC0-2, just because we only have, like now we just reached the 1 year of data. Just a few slides on what we have right now in terms of validation. You are located right here, where this star is, Pasadena, California, and you might have seen the solar dome on one of the buildings nearby when you have been outside. There's an FTS run by Paul's group underneath, and it's basically taking column measurements throughout the year all the time, which is being used as validation site for OC0-2. And OC0-2 has a special mode where they can target the validation site so that we can have optimal coverage within there. And then there's another FTS station in Edwards, California, near this Air Force base here, that does the same thing. And what you see here is probably one of the strongest gradients of xC02 across the globe, because here you have the LA megacity area with really highly elevated CO2 values, whereas here this is really the desert area separated by the San Gabriel Mountains. These are, how many ppm are those? 3, 4? 3 to 4 ppm differences between these sites. So this is just as an illustration of a validation site. If you put all the FTS data together across the globe that are on there, it's a collaboration by many institutions, and have the TCON xC02 on one slide and the OC0-2 xC02 on the other one, you actually already now get a very nice agreement of all the data that we have collected so far. And this is being used to get a kind of a little general bias correction. You see here that there's a little offset. It's really hard to get it immediately right just from first physics, so there has to be some post-processing all the time. But overall, I have to say, if someone would have asked me like 6-7 years ago if he could pull that off, I probably would have said, it's going to be hard. But yeah, we're actually getting to a degree where I think the inverse modelers have to start being a little more innovative as well, because we can't get rid of every 0.1, 0.2 ppm bias. But I think the inverse modelers, we are reaching a state where probably the errors in atmospheric transport are almost equally big as the errors that might be coming from our measurement biases. And B, there might be smart ways of accommodating or fitting potential biases where we know the physical reasons for them in an inversion scheme on the fly, something alongside what Peter Bergamaschi did for methane inversions years ago. Okay. Maybe this might be a little too technical, but one thing that I have to mention is you've seen these nice coverage over the oceans. We do that with OC0-2 by pointing at the glint mode, which is basically kind of a specular reflection at the ocean surface. And the instrument was, in the original approach, it's alternating between a nadir mode every 16 days and then a glint mode every 16 days. The disadvantage of nadir is, if you look nadir over the ocean, you really don't see anything because the oceans are basically pretty black. The disadvantage a little bit if you go glint over land is that you look, if you have the sun at slant angles and you also look at slant angles at it, you really have a long air mass that you observe at, so it's a little bit more susceptible to retrieval biases. In terms of fluorescence, it's also different because suddenly you look at the shaded fraction of the canopy and not really the sunlit fraction of it. So it's basically at the opposite side of the hotspot of vegetation. There's now a revised approach because we've realized that some of these orbits, they basically almost always cross over land, so it doesn't really make any sense to do them in nadir all the time. So these are now being switched to pure glint orbits, and then there's an alternating pattern on land between glint and nadir all the time. Because with this approach, you basically skip the ocean or don't have any information on the ocean for half of each month. And now it's being a little bit more equally distributed in time. And these have been implemented in early 2015. So what's next? OC0-3. Don't bargain with me for power because I'm not really. So I wasn't really aware of all these problems. I'm nicely shielded from that yet. And I also don't have to talk a lot about the ISS orbit geometry because I think a lot of this has been pointed out before. The main difference between OC0-2 and OC0-3 is basically that OC0-2 was really on its own spacecraft, and it did the pointing by just moving the entire satellite. So we point to a specific location on the ground by rotating the entire spacecraft. That would be a little hard to convince the ISS that we want to rotate the entire ISS all the time to point to a specific spot. So they now have a pointing mirror. The advantage is now it can also flip between land and ocean at the glint spot directly. Because before, if you cross over Africa and then you go over the ocean, you can't suddenly rotate a spacecraft within like a second and point at the glint spot. That doesn't work. But if you have a pointing mirror similar to GOSAT, you can actually flip the mirror and directly look at the glint spot when you are over ocean and look at nadir when you look at land. So that's a big advantage. So this is just a quick comparison of them. Maybe the most dramatic one is now we can cover plus minus 52 degrees on the ISS just because of how the orbit works. The best thing is there's an enhanced target mode capability because before we could point only with a spacecraft. Now we have an expanded pointing mechanism with a pointing mirror assembly, and the same holds. This will be great for the target mode, with which I talk about a little bit next, but also the glint and ocean sampling, which will be really optimized because so far we were throwing away a lot of data over the oceans because they are unusable. In terms of the target mode, where basically the satellite can point at a specific spot and then scan over it with what OC0-3 can do, but OC0-2 not really that much. OC0-2 has a target mode where we basically keep staring at something while we fly over it. OC0-3 with the mirror can basically jitter around and basically image the area around it a little bit. Since we are more in an ecosystem related workshop here, I don't talk about one of the main goals, which is big cities that where you might see stronger CO2 gradients. So for instance, you could map the entire LA basin with this mode. But in this case here, you could also just take some interesting areas, either in the tropical Amazon or say the mid-continental area here, the Midwest in the US, and you can basically map the entire area with the OC0-2 target mode completely. So this would be one of the big improvements. And I have a little bit of time still to talk about the byproduct of OC0-2 and OC0-3, which is solar-induced chlorophyll fluorescence. It's kind of like giving the Flex and CarbonSat talk in one go from the Earth Explorer 8 recommendation from last week, I think, where there have been strong fights, of course, between which instrument will fly as the next Earth Explorer 8 ESA mission. And Flex, which will target only solar-induced fluorescence, was actually recommended by the advisory committee and will probably go into space one day. Just to give you a little bit of a nutshell what solar-induced chlorophyll fluorescence is. Once we have the chlorophyll complex and the solar photon hits it, it's being absorbed in an excited state, it can undergo different kind of quenching mechanism. One is, of course, doing photochemistry. What it's supposed to do, one big one here is non-photochemical quenching. It's being basically released as heat, but a certain fraction of the energy is always emitted as fluorescence. And it's typically about 1 to 2% of the total absorbed radiation is always re-emitted as chlorophyll fluorescence. If you would see what we actually see from space, in principle, we have the solar-induced fluorescence would be par times F par times basically the fluorescence efficiency, like the ratio that goes out here. If we do it really in a naive way, this is very similar to the expression of GPP, the gross primary productivity, which is par times F par, basically times the light use efficiency, what we see here. And to first order, we would thus get a relationship which is GPP equals SIF times the ratio of these efficiencies, which is, of course, a tricky part because they co-vary under many circumstances of stress, but they don't always co-vary with a slope of 1. Or very rarely, actually. So this is the more tricky part to characterize, where a lot of research will have to be done in the near future. Just a carbon and water cycle link, which might be interesting for eco-stress. This is a paper from Flexos et al. In 2002, where you had different plans with different stomatal conductances at different radiation levels here. And you see that the fluorescence value from the high stomatal conductance to the lower ones is substantially reduced by up to 40% in this case. So there is a so fluorescence could be useful to measure environmental stress in that way. And ideally, it can be combined with kind of canopy temperature as well. Because for us, it's really hard to disentangle these effects from changes in APAR. It's really hard to do a really process-based understanding of what's going on in this case. I'll skip the GOSATS highlight because I want to move on directly to the year of OC0-2 data for fluorescence. This is what we get from OC0-2 right now with fluorescence just at one of those wavelengths, hoping that this works. And this is now a time series roughly gridded, averaged over 16 days. Green is high. Sorry, this cut off this color scale here. So green is high fluorescence, the red is basically no fluorescence. And now you get the growing season here kicking in. And the Midwest, which is really, like the paper by Luis Guanta has shown, that the area here in the crop belt of the US has the highest peak fluorescence values across the globe. And now you see basically the dormant season again. And now it basically is just repeating itself. But it's nice to see the transition of the growing season here, basically starting in May, June, July, going in there. And then Spain is basically drying out in May, June already, similar to the climate here in LA that you might have noticed here. This is a long-term average that we observe now. This is basically all the data that we have gridded on this map. That's why you get a nice global coverage, but it might be slightly different seasons sampled at different areas. But overall, it's working as we expected it to be with OC0-2. Maybe I'll just quickly go through these because looking forward, we also build a chlorophyll fluorescence imaging spectrometer, which is an airborne version sitting here on a twin otter that we use for OC0-2 validation, but in the long term, of course, also to do research. We actually looked at a piece of sod here where you can see a beautiful spectra. So as opposed to OC0-2, which kind of took up fluorescence as a kind of byproduct just by chance, more or less, we now have a more dedicated instrument where we basically have the whole wavelength range where fluorescence is occurring at a high resolution. And these are all Fraunhofer lines in the sun that we can use for retrieval, whereas for OC0-2, we can only use these two guys here. And now we can use all of them. So we can have an optimized fluorescence retrieval. And this just gives you an example also of how an OC0-2 track actually looks like. So these are two OC0-2 orbits on August 13 and August 16. Overlaid in color scale is the fluorescence value. I always thought it would look way too noisy if I plot each individual measurement, but it's kind of okay. A lot of this is really just precision error, just noise. But these are the tracks that we underflew with the CFIS instrument as well. And if you just look at this one, if you see these wiggly lines here, this is basically from left to right, it's the swath of the aircraft instrument. And we basically underflew that track during the time of the OC0-2 overpass with the CFIS instrument. And this is all very recent, so we are currently working on the data, validating the OC0-2 fluorescence measurements, which would make it the first so far spaceborne validated fluorescence measurement. This is my last slide just for fun because we had a workshop nearby where you basically can see the city Des Moines with the OC0-2 track directly. I would not have thought that we can do it because usually these measurements are pretty noisy. But we see the instrument coming from the Corn Belt and soybean area getting into the city, which is actually rather green. So you see the depletion in fluorescence immediately, and then it goes back up again. And this is OC0-2 data. This is how footprint of OC0-2 looks like, and similar. Roughly 1.3 times 2.2 kilometers. OC0-3 will be very similar. And with that, I'm in the red light now.